Hi, I'm Dr. J, and this is a video about comparing normal means. This is the third video in a three-part series talking all about comparing normal means. But in the previous two videos, we took as an assumption that the different groups that we were comparing normal means for had different variances. And so now we're going to start out in this video by testing that assumption and then moving forward by assuming that all the groups have a common variance rather than different variances. And so this first test that we're going to look at is a test of equality of the variances. And so here we do a test for equality of the variances, and that p-value is relatively large. That means that there is not sufficient evidence to say the data are incompatible with that null model that says that the variances are all equal. And so although other things And so one way that we might want to move forward is to go ahead and assume all those variances are equal, and maybe that makes our life easier, provides more power. And so this is the model now that we're going to be considering going forward, right? And the key difference between these two models, the top one and the bottom one, is there's no subscript on that variance. That sigma does not have a subscript g. Now this is a pretty common assumption, in particular when your group sizes are small. When your group sizes are small, there's actually not much information in the data to tell you about the variances and whether or not they are the same. But it might be helpful to borrow strength across those different groups to have a common variance. But you should make sure that that makes sense in the context of your particular application of these approaches. But now moving forward and assuming a common variance amongst all groups, we can start thinking about testing those means. Notice now the model up there has no subscript on the sigma. That is, the variances are the same across all of the groups. So one first test we might want to do is to test the equality of those means. Here we get a relatively small p-value, and that small p-value tells us that the data seem incompatible with this null hypothesis model. And again, that doesn't tell us specifically what is the problem, and so we might want to go and investigate, right? It might be independence assumptions, normality assumptions, constant variance assumption, although we kind of looked at that already. Or maybe it's really these means not being the same. And so if we go forward and we say, all right, let's assume that these means aren't the same and we want to take a test or we want to compare individual comparisons of those different means, we can do that through the pairwise.t test that we saw before. The only difference here is there was an argument called pool.sd in the previous video, and that defaults to being true. That is, it defaults to assuming that the variance in all the groups are the same. And so by not changing that, like we did last time, we are assuming that the variances are all the same. All right, so we can do the same approach as a Bayesian. As a Bayesian, if we assume that those variances are all the same, now we need a prior over all the model parameters. That prior that we're going to use is a prior that you've seen before, just 1 over sigma squared. That means it's uniform for all the means, and just 1 over sigma squared for that variance. If we assume this prior, it turns out the mathematics are a little bit more complicated because we can't actually just get a posterior for each of the means individually. What we do get is a conditional posterior. So if you'll see that first equation there, the mu subscript g, we condition on sigma squared. And if we condition on sigma squared, we have a normal distribution for those means, unlike the t distribution we had before when we didn't have sigma squared. But now we have that sigma squared, which is again unknown. And so now we have a prior that turns into a posterior for that variance term. It turns out that that has an inverse gamma distribution. It has this shape and rate parameter. And this is going to be relevant in a little bit when we go to draw samples from the posterior distribution for mu. And the way that we're going to draw samples for the posterior distribution for mu, right? Remember that there's not just one mu, there's one for each group. So that whole collection of means. The way that we're going to draw samples is we're going to first draw a variance. Okay, that's the sigma squared. So we're going to draw that variance. Then we're going to plug that variance into the normal that's given right up here. And we're going to draw each of the mu subscript g. Right, so mu1 through mu capital G. So we're going to draw all of those. And then we're going to repeat that whole process. So we're going to draw a new sigma squared and draw a whole set of the mu parameters. And that's the way that when you have this kind of structure, you can draw simulations from these parameters, posterior distributions. All right, so we get something that looks very similar to what we had in the previous video. So this is now a posterior for those means of each of the groups, but here we've assumed that the variance is the same within the group, so it will look slightly different than what we saw before. And one of the main reasons, as a reminder, that we wanted to draw samples is because now we can calculate differences between those samples, and we can calculate posterior probabilities that one of the parameters is greater than the other, and we can construct confident, credible intervals for that difference. Okay, so over the last 3 videos, which were all very succinct whirlwind tours, right, with very, was there any detail in there at all? Maybe not. Right, whirlwind tours of what you do when you want to compare normal means. We basically went through and used the tools that statistical inference provides. We used p-values and confidence intervals, posterior distributions, credible intervals, and posterior probabilities. At this point, there might be another video coming up talking about multiple comparisons, but if not, we're turning a chapter in this course, and we're going to start talking about a particular statistical model called a linear regression model. Hope to catch you for those videos.